Hello, everybody. As promised, here is the YouTube solution key to the pre-calculus review for Unit 6. So let's get right to it. The first four problems say, name the trigonometric function that is equivalent to the expression. So these are pretty straightforward. They should have been in your notes several times. So for number one, 1 over cosine, that is a reciprocal identity. 1 over cosine is the same as secant. For number two, 1 over sine is the same as cosecant, which is CSC. Number three, 1 over secant, that is the reciprocal identity with cosine. Remember, cosine and secant are reciprocals. And for number four, 1 over tangent, or the reciprocal of tangent, is cotangent, which looks like cot. So there are your solutions to the first four. So we will keep on going here. Let's see, clear. And we will go to the next problem, which was number 25. So in this one, in this block of problems, 25, 26, 27, 28, 29, you're asked to verify the identity. So on number 25 here, we're going to take a look at it and try to dissect it a little bit. So the more complex side is the left side. So we're going to try to make the left side look like the right side. So I have a cosine x times a tan squared x plus 1, and ultimately it has to become secant x. So in my mind, the big tell on this one is I see tan squared x plus 1, and I notice that that is a Pythagorean identity. And the tell is the tan squared, or the function squared, plus 1. So I know that the tan squared plus 1 is a Pythagorean identity. It looks like tangent squared of x plus 1 is equal to secant squared of x. So I'm going to substitute, or fair trade, tangent squared x plus 1. That whole expression just becomes secant squared. So I'm going to do a rewrite. So now I have cosine x times secant squared x. That ultimately has to look like and equal secant x. So at this point, what I'm going to do is I'm going to notice that I have cosine right here. And it's generally a good strategy to boil down the problems in terms of sine and cosine. So I already did a Pythagorean identity. So now I'm going to do a fair trade, or an alter ego of secant squared. Remember, secant is 1 over cosine. So I'm going to rewrite my cosine x, and I'm going to multiply and change secant squared into 1 over cosine squared. That's a fair trade, or an even exchange. That has to ultimately look like secant x. Now I'll notice here, and if you want to call this cosine x, if you want to put it over 1, that's fine. I notice that I have cosine on the numerator and cosine squared in the denominator. This cosine up top here divides into itself once, and it divides into cosine squared cosine times. So in other words, it knocks the power down from the second powered squared to just the first power. So if I do a rewrite there, folks, I have 1 over cosine x. I need that to look like secant x. And then finally, I notice that 1 over cosecant, or excuse me, 1 over cosine is a reciprocal identity. 1 over cosine is the same as secant. So now I have secant x equals secant x, and it is verified. So that is the solution to number 25. That may not be the only way to get it, but that was the one that was most apparent to me. Okay, so with that in mind, we will move on to the next one. So we will clear and keep it moving. Okay, number 26. So on this one, we have secant squared x times cotangent of x minus cotangent x equals tangent x. So clearly the left side is more complicated. So in the end, we just want it to look like this, tangent x. How do we do that? Well, if I'm an inspector here, so I look at this term, secant squared x cotangent x minus cotangent x, I notice that the cotangent x is common to both terms. So I'm going to factor it out. Factoring it out is a powerful tool. So I'm going to say, all right, cotangent, you're common to both. So we're going to factor you out, the cotangent of x. Okay, so if I factor it out, I still have my secant squared x. Cotangent x got factored out minus, since I factored out cotangent x, I asked myself, cotangent x times what gets me back to cotangent x? So that would have to be a 1, because if you distributed it forward, cotangent x times 1 is back to cotangent x. And we have to make this ultimately look like tangent x. All right, next, I'm going to take a look here and I'm going to be extremely suspicious about this secant squared x minus 1. If I have a function squared minus 1 or a function squared plus 1, I'm going to be very suspicious that it's a Pythagorean identity. So what Pythagorean identity involves secant squared x? That would be the 1 plus tangent squared x is equal to secant squared x. Now, it doesn't look exactly like what I have here in red, so I have to subtract 1 to both sides, like we've talked about in class. So now, tangent squared x does in fact equal secant squared x minus 1. So now, anytime I see secant squared x minus 1, I can just fair trade or replace it with tangent squared x, which we will do here. So I'm going to rewrite, bring down my cotangent x, and I'm going to replace the expression secant squared x minus 1 with an alternative here, which is tangent squared x. And again, I can do that due to the Pythagorean identity. And that has to ultimately end up equaling and looking like tangent of x, plain tan x. So next, what I noticed is, I'm thinking to myself, what do I know about cotangent? Well, I know cotangent is 1 over tangent using a reciprocal identity times, and I know tangent squared is just tangent times itself. Okay? You don't have to separate it out like that, but it might help some folks see what happens next. If you want to make everything a fraction, you may put those over 1. And ultimately, the goal is I just have tangent x. Okay, going back to the left side, notice that I have a tan x on the bottom multiplied to a tan x on the top. Those cancel 1 for 1. So now I am left with 1 times tan x is tan x. In the denominators, I just have 1 times 1. Dividing by 1 is there's no point. It doesn't change the value. So lo and behold, tan x is equal to tan x. The identity is verified. Check. So that is my solution to number 26. There are other ways you can get to the finish line, but that was the one that came to me first. Okay, so with that in mind, we will clear the screen and go on to number 27. Okay, number 27, we have sine cubed theta plus sine theta cosine squared theta, and that equals just plain sine theta. So in the end, we want the left side to just look like, sorry about that. In the end, we want the left side to just look like this. So I'm going to take a look here and notice that we have sine cubed theta, and over here we have sine theta cosine squared theta. So similar to one of the previous problems, I noticed that I have sine common to both terms. So one of my best strategies is if I have a common term, I'm going to factor it out. So since this one's sine cubed and this one's just plain sine is the most I can factor out. So if I factor that out, I pulled out or factored out or divided out a sine theta from sine cubed. So that leaves me with sine squared. Plus, I factored out the sine theta. So now I just have to bring down the cosine squared theta. And all of that happy stuff has to ultimately equal sine theta. So next, I look back at my left side and I notice here, this looks very suspicious. Sine squared theta plus cosine squared theta, that is the Pythagorean identity. That is, anytime you have sine squared theta plus cosine squared theta, that always just equals 1. So these two just make 1. So I'm going to sub that out next. So I'm going to bring down my sine theta, and I'm going to replace sine squared theta plus cosine squared theta. I'm going to replace that with just 1 due to the Pythagorean identity. And the left side has to ultimately equal sine theta. So now I look and I see what happens. Sine theta times 1 is just sine theta. And lo and behold, it does equal sine theta. So this identity is verified. Check. So what came to my mind on this one is that I could factor out sine from both terms and everything fell into place. Again, your mileage may vary. Maybe perhaps there's another angle to look at this from. This was the simplest and most obvious solution that came my way. Okay, so with that in mind, I'm going to clear the screen and we'll proceed to the next example, which would be 28. Okay, number 28, we have cotangent squared x minus cosine squared x equals cotangent squared x times cosine squared x. So you may be tempted to do something with Pythagorean identities. However, I know that cotangent is just cosine divided by sine, and I already have cosine here. So I'm just going to take a gamble and go down the road of switching this out. Cotangent is cosine over sine. And since cotangent was squared, both of these have to be squared also to keep the balance. All right, so that was a fair trade there. And I'm going to bring down my subtract and bring down my cosine squared x. And in the end, we want the left side to look like cotangent squared x times cosine squared x. Well, what do I notice now? Similar to some of the previous problems, I notice that I have cosine squared x minus cosine squared x. I can factor out cosine squared x because it's common to both terms. Again, if you want to make this a fraction over 1, you may do that. So now I'm going to take my common term, cosine squared x. I'm going to factor it out. So if I pull that out, then I have my sine squared in the denominator still, but I have 1 over that, right? Because if I distributed this back, I'd get back to here. Minus, since I factored out cosine squared x, I ask myself, cosine squared x times what brings me back to cosine squared x? And of course, that would be a 1. So now, ultimately, that has to equal cotangent squared x times cosine squared x. All right, so next, what do I notice? Well, I notice that I do have a cosine squared x here, which matches this guy. And I don't have cotangent squared x yet. So now I'm thinking about, well, what kind of trade or even exchange can I make? So I'm thinking to myself, I'm going to remember boiling things down into cosine and sine are usually good. So I'm going to leave this as cosine squared x. And this is a reciprocal. I know 1 over sine squared. I know what that's worth. 1 over sine is always cosecant. So that's cosecant. And since sine was squared, this is squared as well. Cosecant squared x, bring down my -1. And that ultimately has to look like cotangent squared x times cosine squared x. So again, now I'm extremely suspicious when you have a function squared, a trig function squared -1, be very, very wary that it's a Pythagorean identity. So if I look at my notes, I'm going to fix my cursor real quick. I'm going to look at my notes, and the identity that involves cosecant squared is 1 plus cotangent squared is equal to cosecant squared. That's a Pythagorean identity. Again, note in my parentheses, I don't have exactly this. I have cosecant squared x -1. So if I take this Pythagorean identity and subtract 1 to both sides, then I have it. I have cotangent squared x is equal to cosecant squared x -1. So anywhere I see cosecant squared x -1, I can replace it with cotangent squared. So I will make that substitution. I will bring down my cosine squared x, and I will replace cosecant squared x -1 with its Pythagorean identity equivalent, which is cotangent squared x. And that ultimately has to equal cotangent squared x times cosine squared x. Well, if I look at it, folks, we've got it. The only difference is in pink on the right, cotangent squared is first, cosine squared is second. So I can easily do that since multiplication is commutative and you can switch the order. We have cotangent squared x first times cosine squared x second does indeed equal cotangent squared x times cosine squared x second, verified. Okay, so solutions here, we're breaking down cotangent into cosine over sine. Factoring out is powerful. And then a reciprocal identity, 1 over sine is cosecant. And again, just being very mindful that when you have a function squared -1, it's generally 9 times out of 10 a Pythagorean identity. So look at your notes and see which one fits and make the substitution. All right, that was number 28. I'm going to erase. And 29. This is the last one on this assignment that involves verifying trigonometric identities. Okay, so in number 29, we have 1 plus sine squared theta over cosine squared theta -1. That has to end up looking like 2 tangent squared theta. All right, so my first instinct here, folks, is I'm really tempted to replace this here, 1 plus sine squared theta, using a Pythagorean identity, but that's not the case. I could have sine squared -1. Just if you check it out, it just nothing works there. So now my next idea is I have 2 terms in the numerator divided by 1 term in the denominator. So I'm going to do what I call the split up the fraction technique, which is basically undoing common denominators. So I'm going to take my first term in the numerator here, this 1, and I'm going to put it over the denominator of cosine squared theta, plus, now I'm going to grab the second part of the numerator, sine squared theta, over the denominator, cosine squared theta. Okay, so now I took care of busting up the fraction. I'm going to bring down the -1, and my goal is to get that looking like 2 times tangent squared theta. All right, so what is my next move? My next move is fair trades, nicknames, even exchanges, substitutions, using the identities, however you want to think of it. I'm just going to try something and see what sticks, kind of like throwing stuff to the wall and seeing what sticks. So let's take this here, 1 over cosine squared. Well, that's a reciprocal identity. I know I can always replace 1 over cosine with secant. So that's secant. Since cosine was squared, secant must be squared. 1 over cosine is secant. Plus, well, let's see, what do I know about sine over cosine? Oh, that's the quotient identity. Sine over cosine is always tangent. So that's tangent squared, since those were squared. Bring down my -1, and that stuff has to ultimately look like 2 times tangent squared theta. All right. So I want 2 groups of tangent squared theta. This is my goal. So I want to see tangent squared theta. I see that here. So that's probably good. So the next thing that draws my attention is I have a secant squared and a -1. Remember, 99 times out of 100, when you have a trig function squared -1, it's a Pythagorean identity. So which one do we know relates secant squared? Well, we have one that says 1 plus tangent squared equals secant squared. Well, again, we have secant squared -1, so I'd have to subtract the 1 to both sides, right? So now I can replace tangent squared. Tangent squared theta is literally the exact same value as secant squared theta -1. So I'm going to take this secant squared theta -1, and I'm going to replace that with its nickname, tangent squared theta. Okay, so that was a substitution there, a Pythagorean identity. I'm going to bring down this plus tangent squared theta, and ultimately that has to become 2 tangent squared theta. So note on the left side, folks, what do we have here? We have tangent squared theta, which is like one of them, like one apple, plus another tangent squared theta, which is like another apple. So apple plus an apple is 2 apples. They're not apples though, they're called tangent squared theta, right? Just like x plus x is 2x, tan squared theta plus tan squared theta is 2 tan squared thetas. Lo and behold, that does in fact equal 2 tan squared theta, and this identity is verified. Check. So very, very good strategy in this one. If you have 2 pieces in the numerator over 1 denominator, split it up, make the exchanges using the identities, and then look for Pythagorean identity to take you home. All right. So far, so good. So now that takes care of the verifying identities. So we'll move on to number 37. All right, moving on, let's clear. All right, and 37. All right, so on this one, note that it doesn't say verify, it says solve. Okay, so a little bit different approach here. So we're going to solve. And the key to these is to get the trigonometric function isolated by itself. So here we have 2 sine x minus 1 equals 0. I want to get sine x isolated by itself. So my first step in doing that would be to add 1 to both sides of the equation. So now I'm going to bring down my 2 sine x, and that equals 0 plus 1 is 1. So I'm close to isolating my function of sine x, but I don't have sine x. I have 2 times sine x. So to undo 2 times, I divide both sides by 2. So the 2's cancel. So I have sine x equals 1/2. So remember, don't whine. Sine is the y coordinate on the unit circle. So now I'm looking like a detective. Where on the unit circle, what angle or angles have a y coordinate of 1/2, positive 1/2? So I have that here. I have a y coordinate of positive 1/2. And I also have it here. I have a y coordinate of positive 1/2. So this one has 2 solutions. Our sine value is 1/2 at x, or you could call it theta, is pi over 6. Remember, pi over 6 is also known as 30 degrees. They're synonymous, radians and degrees, kind of like Fahrenheit versus Celsius. And we also have that pesky y coordinate of 1/2 at 5 pi over 6, which is also known as 150 degrees. So there are your 2 solutions to this, folks, pi over 6 and 5 pi over 6. All right, we'll move on and use the technique on the next one, number 38. So if we clear that, here we go. Number 38, same technique. You want to isolate the trigonometric function. So we have tangent of x plus 1 equals 0. So we want to get tan x by itself. So that would be minus 1 to both sides. So tangent of x is equal to 0 minus 1 is negative 1. So what this is asking us is, what angle or angles have a tangent, which is another way to say that is y over x, a y divided by x ratio. Remember, tangent is sine over cosine. Sine over cosine, that's tangent is a substitution, sine over cosine. Remember, the sine is indicative of the y coordinate, the opposite leg on the unit circle, and cosine is indicative of the x coordinate, the adjacent leg on the unit circle. So you're asking yourself, what angles have a y over x ratio of negative 1? Well, the cool thing about this is the only way to get 1 is something divided by itself. And the only way you're going to get negative 1 is if one of those numbers is negative. So basically, you're looking for the same coordinates so that y divided by x is 1, but one of which is negative. And the only place on the unit circle where you have duplicate coordinates are the 45-degree angle, the pi over 4s. So we have that look here, but they're both positive. So if we divide them out, we get positive 1, not negative 1. Okay, so not there. How about here? We would have root 2 over 2 divided by negative root 2 over 2, which would in fact give us negative 1. So that is one solution. We have 3 pi over 4, which is AKA 135 degrees, if you like degrees. Okay, 135 degrees. And do we have this anywhere else? Well, not here, because a negative divided by a negative would be positive, and we need negative 1. How about in quadrant 4? What about right here? Negative root 2 over 2 divided by positive root 2 over 2 would be a negative 1. So that also is a solution. 7 pi over 4, which is also known as 315 degrees. 315 degrees. So there you have it, folks. That is how you solve these trigonometric equations. Okay, now we're going to move on to sum and difference formulas or techniques. So let me clear the screen. And let's look at number 71. So for courtesy here, I have copied the sum and difference identities here. So number 71, it says write the expression as the sine, cosine, or tangent of an angle. It's just going to be one of those, okay? Not all three. So look for patterns. You have sine of an angle times cosine of an angle plus cosine of the first angle times sine of the second angle. So it's sine cos plus cosine. Which of these identities looks like that? It is this one, right? Let's make sure. We have sine A cos B, sine A cos B, plus cosine A sine B. Yep, that's correct. So all we have to do here, folks, is this expression is equivalent to sine of A plus B. So it's equivalent to sine, let me write that a little bit more clearly, sine of A plus B, with the 130 is your A and your 50 is B. It's consistent over here. 130 is A, 50 is B. So we can say that it's the sine of, substitute these in, 130 plus 50. And if we get a sum there, it's supposed to be a 50. If we get a sum there, that is just sine of 180 degrees. Okay. Now, the sine of 180 degrees is 0, but we weren't asked to solve. We were just asked to write or rewrite the expression as the sine of a single angle. So all this fun stuff is exactly the same value as sine of 180 degrees. All right. So I'll leave that on the screen and let me switch colors here. How about blue? Number 72 says cosine 45 times cosine 120 minus sine 45 times sine 120. So it's like a cosine AB minus a sine AB. So which one looks like this, where you have cosine twice minus sine twice? That looks like this one right here. Okay, so it's the cosine sum identity. So all this here can be expressed as cosine A plus B, where 45 is your A, 120 is your B, 45 is your A, 120 is your B. So we have literally cosine of 45 plus 120, and we sum those up. 45 plus 120 is 165 degrees, and that is it. It did not say to solve or evaluate anything like that. It just said write the expression as sine, cosine, or tangent of a single angle, and this one turned out to be a cosine. So not much to see there. Use your notes and use patterns, pattern recognition, and match it up. Okay, with that in mind, we're getting to the home stretch. Now we have double angle and half angles to do. So that'll bring us cruising in to problem number 93. So if I can clear my screen here, sometimes my mouse gets kind of goofy and I can't see where I'm looking. So here we go. 93. All right. So it says find the exact values of sine double u, which is an unknown angle. U is an unknown angle like theta, cosine 2u, and tangent 2u using double angle formulas. All right, so we're going to go through this on 3 separate sides. We're going to do sine, and then on the next slide, cosine, and then tangent. So this is like 3 problems in one. All right, so the information, they tell us 2 things. The sine from the angle is -5/7, and our angle u, again, if you don't like u, you could make it theta if you want. Okay, same thing, it just means the angle. The angle is sandwiched between pi, which is 180 degrees, and 3 pi over 2, which is 270 degrees. So the first thing I'm going to do is I'm going to draw a coordinate plane. going to draw a coordinate plane, and I'm going to label the quadrants. So we have quadrant 1, which goes from 0 degrees to 90 degrees, or pi over 2. All right, I can make that a little bit better. Pi over 2. Quadrant 2 goes from pi over 2 to pi, which is also known as 180 degrees. Quadrant 3 here goes from pi 180 degrees to 3 pi over 2, which is 270 degrees. And then quadrant 4 is from 270 degrees to 360, which is a full revolution, also known as 2 pi. So if the information here, folks, says that our angle U is trapped between pi and 3 pi over 2, we are in quadrant 3. So I'm going to change colors here, and I'm going to draw a terminal side of a triangle in quadrant 3. And then I'm going to draw that to the x-axis and then back to the origin. Okay, that establishes our right triangle to solve this situation. So I can put that this is a right triangle, and our reference angle always butts up to the origin. I'm going to call it U because that was used in the problem. You could call it theta if you wish. And remember, sine is a fancy, funky word for opposite over hypotenuse. So from U here at the origin, the opposite would be -5. The hypotenuse is 7. We don't know the adjacent leg, which rests on the x-axis, but I do know that it's negative because we're in quadrant 3. So again, from the origin, you'd be walking to the left, which is negative, and walking down, which is negative. So both legs are negative. The hypotenuse, by definition, is always positive. So how do we find this missing x leg right here? Well, that would be Pythagorean theorem, a squared plus b squared equals c squared. So we have x squared plus -5 squared, those are our legs, equals the hypotenuse, which is like the radius of the unit circle, even though we're not on a unit circle. Similar kind of thought there, equals 7 squared. So that would be x squared plus 25 equals 49. Subtract 25 to both sides. So we have x squared is equal to 49 minus 25 is 24. Take the square root of both sides. And 24 is not a perfect square, but I'm going to think, is it divisible by 1? So let's see, what perfect squares are smaller than 24? We've got 16. Nope, 16 doesn't divide into 24. 9. Nope, 9 doesn't divide into 24. How about 4? Yep. 4 goes into 24 6 times. So I say, okay, 24, you little rat, you're nothing more than the square root of 4 times the square root of 6, because 4 times 6 gives you back 24. Since the square root of 4 is a perfect square, that's a whole 2. Root 6 is irrational, so it remains root 6. So now this x adjacent leg is no longer unknown. It's worth 2 root 6. But again, since it's in quadrant 3 and it's to the left, that's a -2 root 6. So now I have all 3 sides of my triangle. I have the signs correct. I have it in the correct quadrant. So now we are ready to jam. The problem asked to find not sine of the angle, but sine of the double angle. So we need to use the double angle formula. The sine of twice u is equal to 2 times sine u times cosine u. Well, due to the picture we have, we can easily find the sine and cosine ratios. So now it's very doable. So sine of double the angle is equal to the constant 2 times the sine of the angle. Well, the sine, remember the fancy word is opposite over hypotenuse. So the sign here is -5/7. That's just a replacement of the ratio times. Remember, cosine is a funky word for adjacent over a hypotenuse. So the adjacent leg here is this -2√6, and the hypotenuse is 7. All right. So now I have all my values. If I want to make this whole 2 a fraction, I can put it over 1. So now I have 2 times -5 times -2√6. Let's see, 2 times -5 is -10. -10 times -2 is +20. And bring over my √6 over 1 times 7 is 49. And that is it. Okay. Because 20 and 49 are relatively prime. They don't share any factors to simplify. So my simplest and best answer for the sign the sine of 2u is 20√6 over 49. So that is the sine of double the angle or twice the angle. Well, that brings us next to finding the cosine of double the angle. So we're still on number 93. We're just on to the next part, which is finding cosine of 2u. So let me clear this. And we will go to the next slide, which what I've done here is I've just superimposed the formula for cosine 2u. So there's different options here, but what I think I'd like to do is I would like to use this variant right here, because I already know the sine ratio. Sine is -5/7. There's no radical. It's easier for me to deal with. So I'm going to say that sine of, no, I'm sorry, we already did that. Okay, we need to do cosine. Cosine of 2u is equal to, I'm going to use this variant here, 1 minus 2 sine squared u, and that's it. So now it's replacement. We have 1 minus 2 times sine squared. Well, what's the sine ratio? The sine ratio is -5/7. All right. So now I'm going to have 1 minus, well, here's the minus. Okay, I brought down the minus. 2 times -5/7 is -10/7. Actually, check that. I'm going to go back, and I'm too tired to edit this video. What mistake was I about to make? Let's go all the way back. This wasn't sine, this was sine squared. So when I replace the sine ratio with -5/7, remember our triangle was in quadrant 3, and we had -2√6 was the adjacent. We had -5 was the opposite, and the hypotenuse was 7. So our sine ratio is opposite over hypotenuse, which is -5/7. But this was sine squared as part of the formula here, folks. So if sine is squared, you have to square the ratio. All right, so I caught my error there. And it's too late for me to edit this, so it is what it is. 1 minus 2 times -5/7 squared, you square top and bottom. -5 squared is +25. 7 squared is 49. So now I have 1 minus, remember this 2 here is like 2 over 1. So 2 times 25 is 50. 1 times 49 is 49. Like we talked about in class, if you have one whole minus a fraction, use whatever the denominator is on that fraction and make an exchange. One whole is 49/49, right? One whole is anything divided by itself. So I'm doing that to match this denominator. So now I got my one whole, which is 49/49 minus 50 49ths. So now I've got my common denominator of 49ths. And 49 take away 50, you're in the hole by 1. So cosine of twice theta is worth negative 1/49. So we're reliant on the formula, and then be careful with the algebra and the substitutions, because as I just showed, it's very easy to make a simple little typo or omit something. Very easy to do. It happens to the best of us. Okay, so that's number 93 still, finding the cosine of twice theta. So let's move on and find the tangent of twice theta, or 2u. So now if I go to clear, okay, clear drawings, go to my mouse. All right, so now here we go. Here is the tangent formula. So the tangent formula for double angle tangent 2u is 2 tan u over 1 minus tan squared u. So you can plug that in, but perhaps I could make a suggestion to you fine people. Remember that tangent is just sine over cosine. So it follows that tangent of twice an angle is equal to the sine of twice the angle over cosine of twice the angle. We already have these two values from the prior two slides, the prior two steps. Okay, so I already had an answer, and if you don't believe me, just rewind the video a little bit. We found the value of sine of double u. That was literally 20√6 over 49, right? A little bit of a nasty answer, but correct nonetheless. And just a moment ago, okay, over, we found the value of cosine double u. Okay, and we found just a second ago that that was negative 1 over 49. Now, we have a substitution there based on work we already did, so this saves you in the long run. Now, you guys, a lot of you like to call it keep, change, flip. So remember, dividing a fraction is the same as multiplying by the reciprocal. So you leave the numerator alone. So that's 20√6 over 49. And instead of dividing, we're going to multiply by the reciprocal, or the flip, of negative 1 over 49, which would be 49 over negative 1. Now, this is terrific because we have a 49 in the numerator and a 49 in the denominator. Those cancel. So now I literally have 20√6 divided by negative 1, which is a negative 20√6. So that is the answer to tangent of twice the angle. And to me, that was far preferable than using the tangent of twice the angle formula, which is in the upper right corner of the screen. Okay, so again, this is another option. Since tangent is sine over cosine, it follows that tangent of twice an angle is equal to sine of twice the angle divided by cosine of twice the angle. So if you just went through all that work, why not work smarter than harder and just divide the sine of double angle value by the cosine of double angle value, like I showed on this slide. All right, that does it for number 93. So I'm going to clear. All right, I'm going to try to find the mouse because that disappeared again. Oh, how much fun this screen recording software is, my good people. All right, so that brings us to problem 94, which is the same idea as the previous one. You are only given cosine of the angle is 4 over 5. And we need to find sine of double angle, cosine double angle, tangent double angle. So let's get right to it. So again, I'm going to have to draw a coordinate plane. Okay, I'm going to draw a coordinate plane. So my y-axis, it's a little bit crooked, but that's okay. My x-axis. And note that this time it says I am between 3 pi over 2 and 2 pi. So from the previous work, you should know that 3 pi over 2 and 2 pi, that's in quadrant 4. So my terminal side of my triangle is going to be here. I connect it to the x-axis and then to the origin. So that is my triangle. It is a right triangle because this is right triangle trig. Okay, so there's your right angle, folks. And you could call this theta. I'm going to call it u to be consistent. And I know cosine is a funky word for adjacent over hypotenuse. So the adjacent here is your x leg. That's 4. The hypotenuse is 5. And this is a famous and common Pythagorean triple. If you have 4 and 5, you also always have 3. So this length is 3. If you don't believe me, do the Pythagorean theorem. And since this opposite leg or y leg is below the axis that is negative, that is the importance of this information here with quadrant 4. Quadrant 4, you have a positive x and a negative y. Your hypotenuse is always positive by definition. Okay, so now we have our parameters. So now we can get cooking. So let's start with finding out what is the sine of twice the angle. So we'll use the formula. That's always equal to 2 times sine times cosine. So now we'll write down our constant 2, and now we'll do the ratios. Sine is a fancy word for opposite over hypotenuse. So from here, the opposite is -3, and the hypotenuse is 5. That's the sine ratio times the cosine ratio. Remember, cosine's a funky word for adjacent over hypotenuse. The adjacent is 4, and the hypotenuse is 5. All right, there's nothing to it but to do it. Now we have to multiply. 2 times -3 times 4 is -24. And in the denominators, 5 times 5 is 25. So there it is. The sine of twice the angle or double the angle is -24/25. -24/25. All right. So 1 down, 2 to go. That was sine of double the angle. Now we have to do cosine. So I am going to erase. And the reason I'm not going to clear everything is so we still have our coordinate plane here. And this time we're going to switch to cosine of double the angle. And note that we have alternatives here. We have what's behind door number 1, number 2, and number 3. I'm going to choose to use the first one just for variety. So cosine of double an angle is equal to cosine squared of the angle minus sine squared of the angle. Okay. Well, I know the cosine ratio in this particular picture is 4/5. So that's 4/5 squared minus the sine ratio is opposite over hypotenuse, which is a -3/5 squared. So now I'll square them. 4/5 squared is 16/25. Bring down my subtract. -3 squared is 9. 5 squared is 25. So I have common denominators. So I consolidate to a denominator of 25. Subtract the numerators, folks. 16 minus 9 is 7. So my cosine of twice the angle is 7 over 25. All right. So chew on that for a minute. Chew on that. So the last thing to do is to find the tangent of twice the angle. So again, here I'm going to erase, and we'll work on the tangent of twice the angle. And there's a couple ways we could do this. Oh, all right, here we go. We could use this formula here, which looks a little bit daunting, or we can think that tangent of twice u, which is the angle, is equal to sine over cosine. But if this is 2u, those match likewise. Well, from the previous problem, we already know these values, okay? We already did this. The sine of twice theta was negative 24/25. Let me put my fraction bar in orange, all right? So here's the fraction bar. The cosine of 2u, we did it about 30 seconds ago, and we found that was worth, I believe it was 7 over 25. All right, so now here's our keep, change, flip idea, where you leave the numerator alone. So that's negative 24/25. Instead of dividing with the fraction bar, instead of dividing, you change it to multiply, and you take the reciprocal of your denominator. So instead of 7/25, it's 25 over 7. Okay, note what's happening here. You have a 25 in the top times a 25 in the bottom. Those cancel. So without any further ado, your final answer here for tangent of twice an angle is negative 24 over 7. Bam. Okay, and that is a wrap. I believe that is the easiest and most efficient way to find tangent of double the angle. So that concludes the double angle work. So now we are left with one problem left, number 107. So if I am able here to clear the screen. And find the mouse. Okay, here we go. Last problem, 107. It says use half angle formulas to find sine, cosine, and tangent of the angle. All right, so let's do that. So here we have, folks, here is the half angle formula for sine. So note, if I want to find the sine of 75 degrees here, note that 75 degrees is not on the unit circle. So I have to make a fair trade. So say, okay, 75 degrees, you're not on the unit circle, but if I double it, that's the same as 150 cut in half. Okay, that's a even exchange. So that's why this is called a half angle formula, because if you take a value on the unit circle and cut it in half, you can find something else. All right, and I lost my mouse again. This is just lovely how this works. All right, so since we're working with sine here, we're going to use the formula. It says plus or minus. Well, 75 degrees is in quadrant 1. Everything in quadrant 1 is positive, so we don't need the minus. So we just need the square root of 1 minus cosine of u, which is this part, which is 150, over 2. Okay? That is the formula. So now let's take the square root of 1 minus cosine of 150 is asking you what is the x coordinate at 150. The x coordinate at 150 is a negative root 3 over 2. So that's my substitution there. cosine, or the x-coordinate at 150, is a negative root 3 over 2, and all that goes over 2. That's part of the formula. So now I'll do a rewrite. So now we have square root 1 minus a negative. Minus a negative is positive. So I've got 1 plus root 3 over 2 over 2. All that is under the square root. Now, there's a little old-fashioned rule in math. It says you're not supposed to have a square root in the denominator. So a technique here is to rationalize the denominator. So since we have 2 in the denominator, I'm going to multiply that to top and bottom. I'm still inside the square root. So now what that's going to do is that's going to give us a perfect square in the denominator. So in the denominator, we're going to have 2 times 2 is 4. Okay, 2 times 2 is 4. Now I'd have to distribute this 2 here. I have to distribute it to the whole numerator. So 2 times this 1, 2 times 1 is 2, plus 2 times root 3 over 2. It cancels out this divide by 2 since you're multiplying by 2. So you're left with just root 3. Okay? So now the final step is the numerator has to stay under the square root because it's not a perfect square. But the denominator is no longer underneath the square root because the square root of 4 is just a beautiful whole 2. So that is your exact value for the sine of 75 degrees. The sine of 75 degrees is equal to this. Okay, not a very nice looking answer, but a correct answer nevertheless. So that's the sine of 75 degrees using the half angle formula. So now we will do cosine of 75 degrees and tangent of 75 degrees, and we will wrap this up. All right, so next, I'm going to clear that. Let's see if I can find the mouse. All right, so now we're going to find the cosine of 75 degrees. So using a likewise thinking here, cosine of 75 degrees, it's not on the unit circle. So I say, okay, 75 degrees, you're the same as 150 divided by 2. That's a fair trade. And we're going to use this formula here, which is the square root of 1 plus cosine u over 2. So now we have the square root of 1 plus, again, the cosine or the x-coordinate at 150. I guess I should have put 150 there. Okay, it's getting late. Okay, the cosine of 150 or the x-coordinate at 150 is negative root 3 over 2. That's a negative root 3 over 2. And then divide by 2 is part of the formula. So again, you're not supposed to leave a square root in the denominator. So I'm going to rationalize it by multiplying by 2 over 2. That's going to create a perfect square in the denominator. Namely, that's going to create a 4, which is still under the square root at this time. 2 times 2 is 4. Now I'm going to take this 2 here and distribute it to the numerator. 2 times 1 is 2, plus negative root 3 over 2 times 2 is just a negative root 3. All right. So finally, we have square root of the numerator, which is 2. Instead of plus a negative, I'm just going to call that minus root 3 over, notice that there is no square root in the denominator now because the square root of 4 is just a whole 2. So that is the answer to the cosine of 75 degrees. It's not beautiful looking, but it is correct nevertheless. Okay, that is going to bring us to tangent of 75 degrees. Now note, I could do sine divided by cosine since I already had those, but since they involve roots within roots, Oh, that's a slippery slope for me. So we're just going to knock out the formula. So without further delay, let me clear the screen and let me see if I can select the mouse. There it is. All right. So problem number 107, the last part. All right. So we have the tangent of 75 degrees. Again, 75 degrees is not on the unit circle. So I fair trade it with 150 over 2. So now we can say I'm going to choose to use this variant here. I can say that is equivalent to the sine of the angle here, the sine of 150, the sine of the angle on the unit circle over 1 plus cosine of 150. Okay. Now that we have that, we can do substitutions. Sine is the y coordinate at 150. The y coordinate at 150 degrees is, what is it? Come on, brain. It is 1/2. So that would be 1/2 over, I'll put the fraction bar in red. Okay, and our denominator would be 1 plus the cosine of 150 degrees is a negative √3 over 2. Okay, so now what I'm going to do is I'm going to consolidate. I'd like just one denominator here instead of two pieces. So I can take this one whole. Again, the idea is if I have a denominator of 2 right here, I can express one whole as, yep, you just told me, 2 over 2. Okay, I heard you through YouTube land. So now I can say I have, in the numerator, I have 1/2, okay, over, now I have common denominators of 2, and I have 2 plus a negative √3, which is 2 minus √3. Okay. So next, I'm going to try keep, change, flip. So I'm going to keep my numerator, which is 1/2. And I'm going to, instead of dividing, I'm going to multiply. And instead of 2 minus √3 over 2, that's going to be 2 over 2 minus √3. All right. So now I have 1 times 2 is 2 over 2 times 2 minus √3. So I have to distribute this 2 to both of those. Or better yet, folks, why don't I do this? Why don't I back up a step and notice that I could cross simplify here. I can say I have a 2 on top, 2 on bottom. Those divide out. So I have 1 over, I don't like that color, 1 over 2 minus √3. Now, that is all well and good, but again, the old-fashioned rule in math that you're not supposed to leave a square root in the denominator. So since this is a two-piece denominator, the strategy is to multiply by the conjugate, which is the denominator, but the opposite sign in the middle. So instead of 2 minus √3, it would be 2 plus √3. And whatever you do to the bottom, you have to do to the top to keep the fraction consistent. In other words, to be multiplying by 1. So now I have 1 times 2 plus √3 is still 2 plus the square root of 3 over, when you multiply by conjugates, it's like FOIL. So you have first times first, 2 times 2 is 4. Now note that the outside and the inside will cancel because I'd have 2 times √3 and then 2 times negative √3. Those will cancel. So then I just have the last. I have minus √3 times √3, which is √9, or a whole 3. So finally, I have 2 plus the square root of 3 over 1. 4 minus 3 is 1. Putting something over 1 is fruitless, so it's just 2 plus root 3. Okay, in hindsight, if I would have used this variant, it would have been a little bit better because I wouldn't have had a radical in the denominator. In fact, if I've come this far, I can show you guys what I'm talking about. So I'm going to erase, and I'll show you what would have happened if I would have used the other variant of the formula. You still get the same answer, 2 plus square root of 3. It's just due to the denominator not being a radical, it's a little bit easier. So what if I would have said tan 150 over 2 is equivalent to 1 minus cosine u over sine u. So now check this out. 1 minus cosine, again, is the x coordinate, and we're dealing with 150 degrees, so I should have wrote 150. Oh, holy cow, it looks bad. All right, we're going to make that look a little bit better. 150. Okay, so we have 1 minus the cosine or x value at 150 is root 3, negative root 3 over 2. Negative root 3 over 2 over the sine value, or the y value at 150 is 1/2. So there's no radical in the denominator. That's just going to make things better. So now we have 1. A minus a negative is plus, so that's plus root 3 over 2. And now, instead of dividing by 1/2, we're going to multiply by the reciprocal. The reciprocal of 1/2 is 2. So now I have this numerator times 2. Well, distribute. 2 times 1 is 2. 2 times root 3 over 2, those 2's cancel, so I have my root 3. So there is the same answer, 2 plus root 3, with a lot less work. So there you have it, folks. All the roads lead to the same destination. I am exhausted. I did manage to do this in one take with little flubs here and there. So now let's see how quickly this will upload to YouTube. But due to the magic of technology, you won't be waiting. You'll just wait for me to upload it. So I hope this solution YouTube guide helps. And, feel free to come to my office hours from Wednesday from 9 to 11 a.m. if you need more help. And good luck as you prepare for your quiz, which is either Thursday or Friday, depending on what class you're in. Thank you guys very much, and good luck studying.